Hello physics students. In the last video, you learned what the Biot-Savart law was. The Biot-Savart law allows us to find the magnetic field of a little fragment of wire with current in it. It's analogous to kq over r squared for charge, which finds the magnitude of a little fragment or a point of charge. Well, in this case, the little fragment of current is an equation that gives us the magnitude of the magnetic field all around it caused by that little fragment. And then we can use what I call right-hand rule number 1 to determine the direction of the magnetic field at a particular point. Once we have that, then we can integrate around a whole wire to find the contributions of each little fragment for the net magnetic field of any shaped wire. So in the last video, we found the magnetic field of a straight wire of finite length. In this video, what we're going to do is find the magnetic field of an arc of current like this. Not a circle, but a part of a circle. And there are two main attributes that affect the magnetic field. First of all, we find it at the center of curvature, not somewhere else like here or here. That's too hard of a problem. So we only find it at the center of curvature. And what changes from problem to problem is the radius of this arc. So maybe you might have a bigger radius or a smaller radius, and the angle of the arc, and also possibly the length of the arc, but from radius and theta, that's enough to find the length. So really there are two parameters that affect the magnetic field at this center. So what I'm going to do first is find the magnetic field for arc in general, and then we're going to look at a specific example. So the Biot-Savart law 2, an arc of current. The question is, or the task is, to determine B net at C, which we define as the center of curvature. So we've got this wire bringing in electricity like that, and then it bends sharply at a 90-degree angle here, and then goes along this arc, and then bends along another 90-degree angle, and the current goes this way. The first point is that the magnetic field caused by these two parts of the wire bringing the current in and bringing it away are zero at the center of curvature, because in this case the angle is 0 degrees in the Biot-Savart law, and here 180 degrees. In other words, when current comes directly at a point or away from a point, it doesn't create magnetic field at that point. The only part that creates magnetic field is this arc over here. Now it has a certain angle theta 1, maybe it's like 60 degrees or something, whatever. That changes from problem to problem, and a certain radius. So the first thing we have to do is find the direction of the magnetic field at this point. So with the current coming down like this, it's going to go like this. So I use this right-hand rule. I put my thumb in the direction of the current, and I see my 3 fingers or my 4 fingers go like this over here into the board. So the magnetic field goes around like this, but at this point it goes straight into the board. So we indicate that by drawing an X in this circle, indicating the dB is into the board. Okay, so that's the magnetic field caused by this maybe ds over here. Okay, now next thing I'm going to have to do is find the magnitude of that. I write out the Biot-Savart law. Now this theta is a different theta than this theta. It's the angle between the radius vector and the ds of the wire. So that's the Biot-Savart law written out. The next thing I have to realize is now I have to add up all the pieces of the entire arc to find the net magnetic field. In other words, I have to integrate along this arc. Before I do that, I have to think about, well, is this dB going to turn, and am I going to need to pick any components of this because some components cancel? The answer is no. If I pick another dB over here, or ds, over here, then it makes the same dB into the board. All the contributions of every piece of this wire always go into the board, so I don't need another trig function over here. So before I move on, let me create a pause to allow you to copy this down. All right, so let's move on and fill in some of the pieces. This angle, theta 2 over here between ds and the radius, no matter where you are in the arc, is always 90 degrees. So that's what I fill in there. And that's about as far as I'm going to go before I start integrating. So Now that I have the expression for the dB, the magnetic field caused by this piece, next I need to find by the entire wire. So I have to add all the contributions. Well, that's the integral sign. I took all the constants out over here, and so the mu 0 I, 4 pi r squared, the only thing that integrates is ds. What are the limits? Well, I have to integrate over the arc. So you might know the formula for the circumference of a circle. Circumference is 2 pi r. Well, if you look at that formula, the 2 pi is the angle around an entire circle. So in general, if you don't go the whole way of 2 pi, but maybe you go like pi, then you replace the 2 pi in 2 pi r with just whatever angle you go around the circle. So this is a generalization of the formula of a circumference. The angle in radians times the radius tells us the length around a part of a circle. So 0 to that, that's going to integrate over the arc. This is a really nice, easy integral. It just integrates to s for our limits. Next, we plug in our limits, theta 1r minus 0, and then we simplify one of the radii, and we have the formula for the magnetic field around an arc of any radius and any angle. So I'll create a pause to allow you to copy this down. Okay, now let's look at a specific example where they might give you an actual angle instead of a variable. So that's an example, our first and only example. We're going to determine the net magnetic field at this center of curvature for this wire, which is an arc of current, straight line of current, then another arc of current, then another straight line of current. And the angle that these arcs exist within is pi over 6 or 30 degrees if you want it in degrees. We want to find the net magnetic field over here caused by all these 4 wires. The first thing is these 2 wires, current away, current toward, create no magnetic field at this point. It's only these 2 arcs that create magnetic field. So before I jump into using the Biot-Savart law in this example, I'm going to first figure out the magnetic field of directions of the 2 pieces. So I put my thumb in the direction of this arc of current right here, and then I see my fingers go into the board over here for the magnetic field of this arc. But when I rotate them around, I see that they would come out of the board over here. So this creates this arc over here, which I've drawn red, creates a dB coming out of the board like this. Whereas this arc, if I, actually, you know what I'll do? I'll put this up here. This arc, I have to use the right-hand rule again, and I put my thumb in the downward direction to indicate the direction of the current, and I see that my 4 fingers on this side of the wire go into the board. So this arc creates a magnetic field like this. So what I have to do right away is I see that I have to find the magnetic field of the 2 arcs and then subtract them to find the net magnetic field because the magnetic fields are in opposite directions. What I'm going to do in this case is I'm going to find the magnetic field as a function of r. And then I can recycle the formula I generate for this particular angle and just subtract by plugging in the 2 radii where this is capital R and this is 1.5 r away from our point in question. So let's proceed. dB, here's the Biot-Savart law written out. Once again, the angle is 90 degrees. That's going to be the case in these arcs. You see that any radius vector to any point is the ds and the radius vector are always 90 degrees. I took all the constants out, leaving only the ds. This time our limits are from 0 to pi, the angle pi over 6 times r. That's the limits for our arc length as we integrate along this wire to add up all the pieces. So that's set up. Now we need to go ahead and evaluate that integral. All right, so if you need a moment to catch up, I'll create a pause so you could copy these notes down. All right, let's move on. So the integral, once again, just integrates to s. The sine 90 is just 1. Okay, so plugging in my limits. One of the radii goes away, the pi goes away, right? Pi, pi, radius, radius, and the 4 and the 6 become 24, giving me my magnetic field for this particular angle. Now, I forgot to do a unit check over here. I should have just to show you that this is the right units. We compare the formula to mu 0 I over 2 pi r, the magnetic field, simple magnetic field for an infinite wire. Theta doesn't have any units, so we have mu 0 I on the top, and we do have a meter on the bottom. This formula is good, as is this one. Okay, so the formulas check out in terms of units. Again, that's for a 30-degree angle, an arc. But we've got two arcs, one of radius r, one of radius 3r, 3/2 r. So this one is a smaller magnetic field because it's at a larger radius. So really I should do this magnetic field minus that one to find the net magnetic field out of the board for B net. So that's what I'll do. I'll say maybe B net will equal the B at radius r minus the B at 3/2 r. And so, plugging in the pieces using this formula, we'll see. Okay. So, I need to create a pause to allow you to catch up if you need to. Okay, so let me just simplify this second term. This would be 24 over 3 over 2 is 12 times 3 is 36. So what I could do is find a common denominator, and so let's see, 72 will work. So I could call this 2, oops, not a good marker, so let's try this one. 2 over 72, and this one 3 over 72. If I multiply this by 3 over 3 and this by 2 over 2. So what I have is 3 minus 2 in the top, which is just 1. So 1 mu 0 I over 72 r. Once again, I have mu 0 amps over meters. Units seem to check out. Again, maybe if I messed up with that constant, I wouldn't catch that, but at least the units have the right form. All right, so let me create another pause to allow you to copy this down. All right, so that's the Biot-Savart law 2. Remember, the general process is you use that equation, mu 0 over 4 pi I ds sine theta between the current and the radius, all divided by r squared. That tells you the magnitude, the size of the magnetic field around a little fragment of wire carrying current around at a certain point. Then you integrate over the whole, and you use the right-hand rule to figure out the direction, and then you integrate over the whole shape to get the net magnetic field. That's the process of using the Biot-Savart law for the magnetic field. And again, in this today, we found the arc, the magnetic field at the center here, and it's going to depend on the radius of the arc and either the arc length or the angle. Once, if you know one, you could find the other. And you integrate and you get the net magnetic field. I hope you enjoyed the video, and I'll see you in the next video.